So thank you for inviting me to give a talk here. I was very busy editing my slide because Jack's and then Andrew's talks covered really beautiful introduction and actually connection to the theory and our observations. So here I will give you some overview of some observations. I will also show some of the observations that was already covered in ONC just to compare with intermediate mass, intermediate UV region. So this plot has shown, you've seen this one so many times. This is Andrew's paper, from Andrew's paper. And this actually shows in the y-axis is a G naught, basically the UV background, and in an x-axis actually is a cluster density, and very extreme environment. So in this talk, I would actually say about extreme, strong, intermediate, and weak. What I wanted to show is mainly this intermediate radiation background, but then our covers are strong. And there are some extreme regions with a very strong UV background, very dense, high density clusters with a lot of OB stars. And here you can see that the lupus and serpens and sigma or even is very low right here, but actually has a range of it. So since we already saw this one, I just wanted to show where the NGC 1977, the intermediate radiation environment may be. It's about in the middle. I've kind of pointed here, and then I will actually go back to this point again. This is kind of simplified. It's a similar kind of Andrew's plot, and increasing UV field strength. And you can see that this is actually the density probability for the solar neighborhood. So the same in the y-axis is UV radiation background, and here the orange colored locus is NGC 1977. That's actually, you can see that there's a lot more density here and is more common environment in our galaxy nearby, and not only in solar neighborhood. So basically what happens, and what I'm going to show you here is ONC-like environment here, which is I define as a strong UV compared to that. And this, what I'm going to show you, NGC 977 later, and NGC 2024, they are kind of weaker. So there are different environments, and then I'm going to show this in 977 because that's where we find something called droplets. Okay, but going back to Orion, this is like popular place, popular life for us. Here is the Orion belt, and actually in all this area, it's pretty interesting. Can show you there's NGC 2024. You will hear from Tom's post. There's a poster by Tom Howarth, and then I think he's going to talk too. And here's 1977 ONC. They're siblings. This is Orion A. You just heard about Orion A, and then here is the Orion B cloud, and 2024 actually is younger. So here's another plot, figure showing that these regions that I'm going to cover, ONC is strong, and then, excuse me, in 1977, which is actually dominated by B star, no O star there, and then there's Sigma Ori that I'm not going to show the result from that, but location is right there, and then it's like 2024. These are the places we see photoevaporating disk observationally. Okay, briefly going over again, I did not include H1641 because I knew that it was going to be covered by a book, but this actually provide a pretty weak environment. So here is ONC M42 that provides strong, intermediate, and weak radiation environment for that 1641. Before I do that, I wanted to mention about the age as well. For this region, there are a lot of studies, and especially my previous postdoc, Min Fang, has done a lot of work, and Marina Kankar done a lot of work as well. So there's a lot of work going on for individual stars. We take the spectra with not only imaging, and then actually we try to put them into the HR diagram, and there's a kinematic information to actually learn about the ages distribution, and there's also kinematic distributions as much as we could. So here in the right-hand side, I actually showed that the age uncertainty is huge. Factor 2 can take that. But I just wanted to show you that ONC, which is shown here in blue, NGC 1977 and H1641, which are three actually represent three different radiation environments. They're about the same age. Okay, and then you have seen this one a lot as well, the disk lifetime constraints. This is the inner disk fraction versus age. And the left-hand side is from Davide Fedele et al. Showing two different types of excesses. So the red one shows accretion disk fraction, and then the blue one is actually dust. So what we see from HRFA or gas measurements and dust have a different, seems like evolutionary path slightly. And then the right-hand side, these are work from our own work. It's in preparation. And ONC is about 1 million year. Well, depending on the model, it could be 1 or 2. I would stick to a younger age that everybody was using here. So it's about 1 million year. Here's on the right upper right-hand side, I see the age uncertainty. You can see there's 1977 ONC, they're similar age, but this fraction is different. So 1977 has only B star, ONC has O stars, and 1641 does not have massive stars. So you can see the differences in the inner disk fraction. Okay, and I'm going to show you some of the proplet images. So proplets are direct evidence, and also is our wonderful lab to study external photoevaporation. That actually how environment is directly impacting the photoevaporating disk. So that's a kind of rare thing. It's very important lab because you can actually, which one actually ionizing that disk. So here's one example actually Andrew also mentioned is TFTS2020. I wanted to briefly mention about extreme cases of UV background. It has, or in this case, ionizing sources are like 6, so there are 6 O stars, there are 1,000 B stars, O3. So Orion, ONC is O6. In this case, there are 2 O3 and more of them. So it's actually quite distant, 1.7 kiloparsec is about 1 million year as well. And this work is from Minfang. And there are 5 known proplets. They're a bit larger, they're kind of larger than ONC cases because it's distant. And you can see that there are 4 proplets discovered. And definitely it was shown that this fraction is very low in this region, and 30%. In strong UV ONC UV background, it's an ONC, of course, you've seen it so many times. And here I would like to show the Josh Eisner et al. Is our ALMA result. And in this case, I only show the disk radius, outer disk radius. And most of them seem to be about 20 to 30 AU, and very small number of them shown to have a large one. For this ALMA region, it doesn't cover entire ONC, the trapezium, very central part actually. Okay, now I also show you here because we talked about the aging discrepancies, and some of them look older than the other. There's a caveat, and when even in trapezium, when we talk about very central Orion, we see the huge age spread. And is it really age spread? So I wanted to show you here about the luminosity spread right here. Okay, so in the right-hand side, there are some SEDs with inside of these proplets. These are all SEDs for the proplets. You can see they're all various kind of excesses from the proplets. Some of them even don't show much excess at all. How do they affect? Some proplets, they are same age, around the same ionizing source in this very central part. And here in HR diagram, they show everywhere. So they are similar age, but depending on the disk orientation and the extinction, these are all extinction corrected, by the way, because we have spectroscopy and we have taken care of veiling. So this luminosity spread is there. And even the very young model, 0.5 million year, doesn't fit some of the very low mass ones. These actually get fitted better with a magnetic model, which actually gives a little bit older age. So that's I wanted you to have that in mind when we discuss age. Now I'm really going to talk to you about the NGC 1977 that represents intermediate UV background. So Running Man Nebula is cool. I don't know if you can see the Running Man here. Most of the stars are B stars, A stars. Those are the massive stars. And then we have a lot of low mass stars. And the right-hand side and lower panel, I show a lot of stars that we have done spectroscopy, optical and infrared imaging, and X-ray imaging analysis for this. And then the blue stars actually show the locations of the B and A stars. So NGC 1977, and the strongest one is right this one, the B1. And the propolis found so far is around this star because we haven't really surveyed the entire region. We only surveyed a part of even one half of the left-hand side of this B1 star. Age is about 1,000,000 years, similar to NC. And stellar density compared to NC, which is like 1,000 per cubic parsec, is about hundreds. This correction is about 80%. This is preliminary work, so it's going to be ready soon. Okay, and here is the image of the photoevaporating disks. In the left-hand side and above is pretty complex. John Barley published this one in 2012. Has us one proplet actually is 0.4 parsec away and evaporating. This is toward 40. The arrow here show actually 42 Ori. That is 42 Ori is the B1 star, and it has a really complex things that we're going to follow with this. And the right-hand side is from our paper in 2016 shows 6 propolis evaporating away from that B star. It has they're all within 0.03 or 0.3 parsec because that was basically how far we went with HSD, John Barry's data. And disk sizes for the 2 resolved disks, number 4 and number 5, they're about 40 to 70 AU. These are the H-alpha images from HSD, and we do not have ALMA, unfortunately. I was scheduled, Ryan Boyden was leading that. We didn't get the data. Yeah, so we're gonna go further again. So the YSO mass for 4 and 5, we have a deep infrared imaging, is very small, 13 Jupiter mass or lower. So these are what we need to definitely follow up with that. And here's another reason. Tom has a poster talk about it, and he may actually cover his talk. It's an NGC 2024. So this is not as low as intermediate background as NGC 1977. It's a slightly it's higher than that, but it's actually lower than ONC. So here is actually image. Actually, this is actually show you where the propolis are. So the proplet 1, proplet 2 around IRS1, which is a B star, and there's IRS2, which is binary, and in the left-hand side with 2 reds represented by 2 red stars, the O8 and then B binary. And then here are some of the propolis that's found. There are 4 propolis found and 4 that we call it candidates. So they appear in here left-hand side with a higher discretion, the right-hand side is a little lower discretion. And the age is very left-hand side. I mean, they are pretty young, younger than probably UNC. They're very embedded. We are working on their spectroscopy, but we do not have many spectroscopic data for many of these. Here's the first one, proplet 1 in H-alpha imaging from HSD. Again, this is a work in preparation. I mean, submitted. It's a preliminary, but you're going to see that in Tom's poster. So here's IRS1, and then you can see that there's a possible jet and then photoevaporating proplet. So this one's a B0.5, slightly more massive than NGC 1977's B star. The age is very young, and we still see that some of the observations here. And there's a proplet 2 and 3. You can see that the direction toward IRS1 and IRS2. So here, please do not share this plot because we're still, it's not accepted yet. So here I showed you Tom's paper about NGC 2024, dust mass versus the projected distance from IRS1 upper panel, and then IRS2 a lower panel. And then 2 blue dots are basically the propolis. You can see the images, the ALMA data actually is from Pantareska et al., the recent one. And here you can see that decreasing disk mass toward the IRS1 source and IRS2 about for the lower panel. And then we actually see some of the more massive ones probably, and then the lower hand side, the propolis actually is one actually pretty well mixed in with the other disks. So now I'm going to actually go back to ONC. I don't know if I have enough time. Orion Nebula, the trapezium. When we actually talk about the most massive ones in ONC, is theta 1 C, which in the left-hand panel, you can see that's here you can see the C, and that's the most massive star, O6. But then there are some B stars, early B stars as well, and that's one I wanted to show you here. It's the HH508, which on top, that's a theta 1 B, that's a B star, and it's slightly further away. You can see that. You see here, or B is a upper right-hand side, and you can see A and D and E as well. There was a paper by Wu et al. So that's what we worked on 2 years ago, and it had a AO imaging of, AO imaging hasn't been shown yet. This is AO imaging of propylene right around the B, not that one C, that one B. You can see that there's a microjet, and there's a B over here. That's the B1 and B5 that are one, that's binary. And you can see that even that is binary star here, B2 and B3, and you can see the HH508 with the tail blowing away. For in the middle panel, that will show you where B, B is. It's about in the, I don't know if you can actually see my, probably cannot see my pointer. So there are two sources, and one of the actually, this tail direction shows a weird morphology. It's right next to B star, but it's still a lot more vectored. It seems like they're on C that is further away, because UV, far UV and EUV both contribution from C is a lot stronger. So even if it's very B, so this in this case, this disk is affected by both B star and Theronori C. One interesting thing that AO imaging that I wanted to actually show you, this is actually around Theronori C, where there are 3 data. And in the middle, you can see that this is H alpha image, but then in the middle, you can see that H alpha blob appeared at that time. It was a clear detection and went away. So there was some kind of transient event happening to the droplets. It has jets. And so actually each proplet has pretty different conditions. Some of them are even binary. So I wanted to actually then later at some point, I hope we can discuss these questions. So we have a lot of the droplets that are mostly, all those droplets we know are mostly from Orion. So why most of the known droplets are found in Orion? Is that what about the other similar age clusters near the stars? So I have had some students and we were trying to find other regions, and we found that a lot of HS images were not deep enough, not as anywhere close to the quality of ONC data that we found a lot of droplets. 1977 was directly observed by John Bali to search for the droplet as well. And then 2024 was actually shown that image was from partial alpha image from near infrared. Those were deep, well-targeted observations. So the question is, how do we then find more samples? Because in order to do statistics, we need some more sample to do it. So that was the one discussion we wanted to do. And for older region, Sigma Ori has one photoevaporating disk that's suggested to have from Viliaco et al. One spectroscopic study that the mass loss rate is about 10 to the minus 9, I think, sort of mass per year. So that's, for instance, the older age, different age, the harder to find because all those photoevaporation has been already done. This would have, you know, this would have lost a lot of mass. It would be hard to actually follow up with those observations in gas, especially. So different range of strong, intermediate, and weak. We can all try to find it, but how can we do that effectively? And then what about the appropriate lifetime? Actually, Andrew talks about this one in one of the papers. And the lifetime is supposed to be very short. So I study the accretion rates for all entire Orion A. They vary a lot, but 10 to about 10 to the minus, the strongest one is 10 to the minus 8 solar mass per year, and then 10 to the minus 9. So how about that? Appropriate lifetime implication for planet formation. So I wanted to actually then draw your attention to Ryan Boyden's poster, where he also talks about the ONC dust and gas how do they look different? So the dust mass and gas mass seems to be lower. Um, the size of the gas disk actually is quite different too. So please go and find the Ryan Boyden's poster, and I think I'm going to stop here. Take away. So the proplyds are found, takeaway points, proplyds found in the B star as well, and then 97.7 was so far the lowest radiation field that we have found the proplyds. There are a lot of discussions to be done and observations to be done for the disk size, disk mass loss, and survival time. And we have future observing proposals and programs going on to actually study more of this.